All right, well, hello everyone, and welcome to the third episode of Selective Attention, where we talk about deep learning research. My name is Sam. This is me. Hello. And joining me, as always, is Andre.
Hey guys.
We are two deep learning researchers who work for a startup in London, and today we're going to talk about extractive question answering. So last week we talked about selective question answering or answer selection. And also gave a brief introduction into the whole field of question answering as a field. I really recommend having listened to that if you haven't already. And today we're going to go over something slightly different to selective question answering and just go really in depth into one of the papers. Just as a warning, this podcast isn't really for beginners. If you are new to deep learning and machine learning, we'll very soon have a site up where we're going to forward all of the best blogs where people have explained things like LSTMs and convolutional networks in a much better way than we could ever do. This is really for people who have a current working understanding of deep learning and are interested in, I guess, finding out a bit more about what the state of the art is and what is actually going on inside these big networks of today that do these crazy things like extractive question answering. So as like last week, I won't be driving today. Andre will be driving. So without further ado, Andre, take it away.
Okay, hey guys. So last week, or last time rather, we talked about extractive question answering, but we focused on selective question answering. This time we'll actually focus in on extractive question answering, and we'll actually repeat the example we looked at last week, which was our sort of motivating example for extractive question answering, and I have it right here. And then we're going to go over a paper which proposes a model which solves this task. So, extractive question answering. In extractive question answering, we are given a passage of text. This is often called the context. We're also given a set of questions. For example, given this passage of text, which was taken from Wikipedia, it's about Kenya. A question might be, where is Kenya located? And then our task is to highlight the correct answer. And what I mean by highlighting the correct answer is we want to find the start and end index of the answer, where the answer is usually contiguous, or in the case of squad is always contiguous. So let's look at three questions given this passage of text. We have a passage of text about Kenya, and the first question is, where is Kenya located? So let's read the passage. Kenya, officially the Republic of Kenya, is a country in Africa and a founding member. So Kenya is a country in Africa. So where is Kenya located? It's located in Africa. So in this case, the start and end index would be the same. They would both be pointing at Africa. What country borders the south of Kenya? Can Rift, and so on, and further southeast of the Indian Ocean. And then it says it is bordered by, am I pronouncing this correctly? Because last time I mispronounced it, it's Tanzania?
That's right,
Tanzania.
yeah.
See, in Slovene, and I'm Slovene, we say Tanzania. So it is bordered by Tanzania to the south, Uganda to the west. And the question was, what country borders the south of Kenya? Well, it's going to be Tanzania. So let me take a different color and highlight it right there. And then the third question is, what was the population of Kenya in 2014? And at the very end, you'll read that that Kenya had a population of approximately 45 million in July 2014. Now, we could argue that the answer here is 45 million, but it could also be approximately 45 million. And in Squad, you're given a set of sort of potential solution answers, and if we went and looked at the answer to this question, it would probably also contain approximately 45 million within that answer set. In this case, notice that as opposed to the answers to the previous two questions, the start and end indices are not the same. So in this case, the start index points here, and the end index points here. And those are essentially the two numbers, the start and end index, which we want to model. Now, just a few more quick words about Squad. So this is taken from Squad. We'll link to Squad down below. It stands for the Stanford question answering dataset. It was released a couple of years ago, and it's become one of the canonical extractive question answering datasets that groups from all around the world have been competing on with their respective models. And in fact, if you go to the Squad website, you'll see the current leaderboard. If you so wish, you can code up a model yourself, submit it to Squad, and they will come up with, they will evaluate your model and then place it on the leaderboard, and it's quite a fun thing to do. So let's look at a particular solution to extractive question answering. But before that, maybe a couple more words about extractive question answering. Why do you think it's interesting? How is it different from selective question answering? What does it mean in terms of application?
Yeah, I mean, I think the interesting thing about extractive question answering is how you might apply it in the real world. So if let's say you're a company and you're trying to build a knowledge bank. So you're trying to scrape something like Wikipedia, and for each country in the country Wikipedia page, in all of the Wikipedia pages that have countries in, you might have a bunch of questions that you're interested in. So you might say, well, for all of the countries, tell me what is the capital, what is the population, what is its major market in the economy, what is the thing that generates all the money for this country. And what you could do is then just have a model scrape through Wikipedia, and just by writing these natural language queries, you'd be able to extract all of that information, which is a pretty useful thing. It's a way of essentially finding the correct answer in a huge knowledge bank without having to pay someone to read it. You just have a model to do it automatically.
Let's look at a particular model, and this is a paper from iClear 2017. When was iClear 2017?
It's usually April, is it?
Yeah.
Yeah.
So almost a year ago now, which means that these guys must have worked on it the year before. And this is from the University of Washington group, but together with the Allen Institute for AI. By the way, the Allen Institute for AI has a podcast itself, and we'll link to them below as well. Notice that we are finally doing an entire episode on an attention model in selective attention. I think that's great. I think there will definitely be way more attention models to follow, and hopefully we'll do an entire episode on attention just by itself. But for now, let's look at a very particular solution to how these guys solve Squad and how they come up with the start and end index. So if we turn to page 2, and I encourage you to either have a printed copy of the paper with you, or at least open it up and have a quick read through. If you turn to page 2, you'll see that they outline in section 2, they outline the 6 steps of the model. And we are going to go over each and every one of these steps, but we'll especially focus on step 4, which is the step to do with attention. So let's just describe very briefly each step. We start with step number 1, which is called the character embedding layer. And in the character embedding layer, you somehow embed the characters for every particular word. The reason why that's useful is because obviously characters within a word actually contain a lot of information about that specific word. For example, the capitalization of the word. This is something which oftentimes word vectors ignore. Number 2 is the word embedding layer, which maps each word to vector space using a pre-trained word embedding. So I think the pre-trained word embeddings they use are glove vectors, but they could have as well used word-to-vec vectors or any other pre-trained embedding.
I guess another important thing to note, right, is along with case sensitive, whether or not a word is capitalized or not. The character level embeddings also help if you have a word that's out of vocabulary. So if you have a really rare word or something like a number, the word level embedding for it will just be the embedding of this does not exist inside the vocabulary that we can deal with. But you actually have like a secondary character level embedding that gives extra information.
Exactly. So yeah, character level embeddings have proven to be very, very useful in all forms of NLP. And they're very, very often used in combination with word embeddings. So once you have the character and word embeddings for every word, you then combine them somehow, and then you pass them through this contextual embedding layer, which is step 3. And the contextual embedding layer is nothing but a bidirectional LSTM, which takes as input the combined outputs of step 1 and 2, and outputs contextual embeddings of the question and passage. So we'll see that in a second. Step 4 is the actual attention mechanism. We'll be spending most of our time on step 4. So this paper actually introduces a nice twist to how attention is normally done, and it also claims that it is because of step 4, essentially, that this model performs well. And then step 5 and 6, so step 5, the modeling layer, is just sort of an intermediate layer which prepares everything for the output layer, and then the output layer is a layer which takes these embeddings of the context, of the squad context, of the passage of text, and then provides us with hopefully the correct start and end index. And then we extract whatever is between the start and end index. We compare it to the correct answer, and hopefully it is the correct answer.
So you have your context, you have your question, you have your sequence of atemporal embeddings. You then make them temporal by putting them through a bidirectional LSTM. So you have your contextual embeddings H and U. You then build an affinity matrix with this parameterized affinity function, which is a highway network, right? We then have our affinity matrix. We then use a match LSTM style attention to build a attended weighted sum for every word in the context with respect to the question words. And then we build a global attended weighted sum of the context with respect to all of the question words. All of this happening with these crazy concatenations with element-wise multiplications. We then produce a massive matrix G, which is the same length as the context, in which we just concatenate everything under the sun that we have that's also of length T. We then get that G, put it through another bidirectional LSTM, and we then use the concatenation of G and M to look at to find P1, and we find P1 by concatenating G and M and then collapsing it with a parameterized vector, and then we find the end index by getting M and G, but it's not M, it's M2 because there's another bidirectional LSTM out of nowhere, and then we collapse it with another parameterized sum to get P2, and that's it.
Step number 1 is the character embedding layer. So remember, in Squad, you were given a passage of text just like this, and then what you do is you tokenize this text, so now you have a list of words, and every one of those words is comprised of characters. You then, usually what you do is you the character inputs are one-hot representations of your character vocabulary. And usually the character vocabulary is quite small. It's nothing as large as the number of words you have, which is why a lot of other people, for example, in NLP have been looking at using only character level embeddings as input. And then you take these character level embeddings of every one particular word, and you combine them somehow. And in this case, they combine them using a convolutional neural network, but I've definitely seen people combine character level embeddings using an LSTM, or even just adding them up. So if you're interested in exactly how this is done, take a read at step 1. In step 2, the word embedding layer, this step is very simple. So in this step, we take a whole bunch of pre-trained word embeddings, and then given a word, we associate it with its vector, with its pre-trained vector representation. So this is another very, very common step within the NLP research community. And then the character and word embeddings are combined using something called a highway network, and we end up with two sequences. We end up with an embedding for the passage of text, and we end up with an embedding of the question. So let's actually start writing this out. We are now left with an embedding of the passage of text, which we will call X. So let me see if I'm getting this right for you guys. Yep. This is the embedding of the context. The context is just the passage of text. So, I mean, context might sound slightly confusing, but it's the way Squad defines the passage of text. Now, the dimensionality of this embedding is d times d by capital T. T is just a time component. If you were implementing this, T would usually be the max length of your passage of text. And then if your current passage of text didn't come up all the way until T, then it would be padded with just some zero vectors or something. The D here is the actual dimensionality of the embeddings. So were you to only be using word-to-vec embeddings of 100 dimensions, D would be 100, but in this case, D is usually something else because you are now combining, you're concatenating, or you're combining in some way character level embeddings as well. And I'm not quite sure what dimensionality glove vectors are. So D, you can think of D as just, it's just some number. And maybe another way of sort of more visually thinking about this is that you have T columns like this, or T vectors like this, and their height is D. Okay, and this is the context, which is just the passage of text. On the flip side, you also have the embedding of the question, and in the paper they define this to be capital Q. Again, the embedding size is the same, so it's just D. But this time, because the question and the context are two different pieces of text, instead of having capital T, we have what they call capital J here. And again, capital J in this case would usually be just the max length of all your questions. And again, if we draw this out, you would end up with something like this. So this is step 1 and step 2 done. Let's move on to step 3. So in step 3, they say, okay, so now we have a embedding of our context and an embedding of our question. Let's pass it through an LSTM to contextualize those embeddings. So if I take a different color, actually, you know what, I'll just do it with the same color. We pass this through an LSTM, or a bidirectional LSTM rather. And we pass this through a bidirectional LSTM. We end up with what they call H, capital H, of size 2D, and capital U of size 2D times J in this case. And you'll notice that oftentimes the output of the LSTM will be a lot smaller than its input. In this case, they're not doing that, and in fact the output is twice as large as the input. Another way of thinking about this is that the input of one of these LSTMs in the bidirectional LSTM is just D, so they're essentially preserving the size. And this is quite an interesting sort of thread which runs throughout their paper whenever they use an LSTM essentially. So we now have capital H and capital U. Capital H is now our contextualized context embedding, and capital U is our contextualized question embedding. How would you describe these? What does a bidirectional LSTM do in this case?
So I guess the aim, what would the sort of the end result of these trained bidirectional LSTMs do is, the input to them are word embeddings, and they're ordered, but each of those embeddings themselves, they don't have any sort of temporal information in them. And the aim of the bidirectional LSTM is to say, for each word that is ordered in this sequence of embeddings, I now want to have, for that word, instead of just a normal embedding, I want to have a contextual embedding. I don't want to overuse the word context, but an embedding that puts that word in context, right? So, you'd think that if you have new and York, where you just have the sequence of embeddings new and York, they themselves would be very different to their contextual embeddings of New York being a place. And once a LSTM has sort of seen them next to each other, you would add like a different context than you would just having these sort of atemporal embeddings in X and Q.
Exactly. So, just like before, we now have slightly larger list of this time contextualized embeddings. So 2D here. J here and 2D here, except this time each one of these contextualized embedding vectors actually contains information about information both in the past and in the future, so both behind and forward from it, as opposed to these embeddings over here, which are just very simply word embeddings plus character level embeddings, but they don't contain any information about any of the surrounding words. This is why LSTMs and bidirectional LSTMs have really become sort of workhorses within NLP over the past couple of years. All right, so capital H, capital U, contextualized context embedding and contextualized question embedding. From now on, I'll probably just call them the context embedding and question embedding. So maybe if I move this paper up, there we go. This is what we have now. And now we get to step number 4. So step number 4 is where these guys introduce their attention model. And let's just look at where step number 4 is. So step number 4 is here. And if you carefully read it out, you'll see that this entire section hinges upon this similarity matrix S. So before we go into the sort of intuition and rationale behind what it is they're doing, let's first describe just what this S is. Capital S, a component in this matrix, capital S, Tj. So this is the tth row and the jth column, is equal to some function alpha of capital H, which if you remember is just the context embedding, capital H, and then the tth column of capital H, which is just the tth embedding, right, of capital H, so of our context embedding. And so alpha is a function of that, and U, capital U, J here, so the jth embedding of our question embeddings. And this is just a single number, so this is a scalar It belongs to the reals. I think the first thing that struck me about this is that this notation is very, I kind of like it. It's very Pythonic.
Yeah, yeah. It is NumPy.
Yeah, it is NumPy notation. It's quite cool. So, this colon here is basically saying sort of consider all rows, and then T here is saying consider the teeth column, right? So consider all the rows, and then consider this one particular teeth column. Same thing goes for the notation here under U. Okay, so we still don't really understand what S is. We know that a single component in S is a function of these two vectors. So what is alpha? So how do they define alpha? So the way that they define alpha is they say alpha is, alpha of two vectors, H and U, is equal to some parameter vector, or some transpose parameter vector, like this, times, or inner product of H, so the first vector, concatenated with U, concatenated with H, element-wise multiplication U. And I think one way of thinking about this is a form of, we're trying to learn the sort of similarity between H and U. I think a better way of maybe thinking about it, instead of calling it a similarity, is to think of it as an affinity. And essentially, we have this just parameterized inner product between a parameter vector, which we learned during training, and the two vectors we give to alpha, which are the teeth sort of context embedding and the J question embedding. So we end up with this large matrix S. And well, I mean, I think one of the things that both Sam and I noticed when we were reading this was this element-wise multiplication here, right? So, this makes a lot of sense. This is kind of confusing, at least for me. I guess maybe one way of thinking about this is that you're trying to consider both H and U and some interaction between H and U, and parameterize the whole lot. And perhaps this interaction between H and U, I mean, this very well could have been some other operation on H and U, might somehow tell you something more about the how H and U interact. Right? Let's just draw out S visually, because I think all this notation, at least for me, is sometimes quite confusing. So if we draw out S here, we can think of S, and I'll try and be as sort of as relevant to the actual lengths of contexts and questions here as possible. So we know that contexts are usually longer than questions, right? A passage of text is usually longer than the question. And now the question is indexed by a capital, is of length J, and the context is of length T. S is comprised of TJ pairs, so we know that S will look something like this. So you can think of this as S. Now, what do you think S? How would you describe sort of what S represents?
So I guess you consider it something like an affinity matrix or similarity matrix, as they call it, the big S for similarity, where you essentially have inside that matrix the affinity between every contextualized word embedding in H to every contextualized word embedding in U.
Mm-hmm. Maybe let's consider just a couple of examples here just to make this slightly clearer. You know, this guy, this component over here is S11, and this would be the affinity between the first context embedding and the first question embedding. And that is essentially what S is. So it is this affinity matrix or similarity matrix or whatever it is you want to call it. The model which this paper proposes then goes on to act on this similarity matrix and attend to it in different ways. Yeah, so that's the similarity matrix. Now let's introduce their attention model. So you're given this S. Remember that all the components in S are learned because you have this parameter which you're essentially calibrating during training. And then what the guys in this paper introduce is two forms of attention, or sort of two directions of attention. So the first direction of attention they call context to query. So let's write that out. In context to query, what they're trying to figure out is which query words are most relevant to each context word. So what does that mean? Again, let's just sort of describe the maths, and then we'll look at the intuition. So what they say is consider a vector small a t belonging to or of size j. So it has j components, and remember j is the length of our question embeddings here. This vector has certain properties, and it has one of its properties is that were you to sum up its components, and remember j here goes from 1 to capital J, so j1 to j. If you summed up its components, it would equal 1. Right, so you can think of this as a distribution across something. We'll get to that in a moment. Now, the way this small a t is calculated is as follows. So they say that at is equal to the softmax of ST, and that this belongs, or this is of size j. Okay, let's stop here for a moment. Remember S is our affinity matrix, and using this NumPy style notation, T here is the tth row, and the colon here signifies consider all columns given the tth row. Now, obviously, that's going to be of size j, and if we go back to our visual representation of the affinity matrix here, which is partially covered, let's consider a particular row. This is a very dark green. Seems black there. So let's consider the tth row here. So this is t. You'll notice that this vector is obviously of size j, and because it's softmaxed, its components will add up to 1. So this property holds if we calculate at like this. Moving on, what they then do is they say, let's somehow use this at, right? Let's use this at in some weighted sum to, get some new matrix, and we'll explain the intuition behind that in a moment. But let's first see how they use it. So they say that, they construct a matrix they call U tilde. A particular column in this U tilde, they say, is equal to the sum across all the components of the corresponding AT. Again, we're summing over its components, so we have the second index here, times U, the corresponding embedding, the corresponding jth embedding in U. And remember, U here is the contextualized question embedding from before. So this, what this is saying is, oh, and by the way, this means that U tilde belongs to, or is of size 2D by T, which is, by the way, is the same size as the context embedding here, right? Context embeddings here. Whoa, this is confusing. I mean, I'm confusing myself now, basically. But this is very much what modern deep learning and NLP looks like today, right? You can imagine that if you're implementing this, there is quite a wide scope for getting a lot of stuff wrong. But let's look at what exactly this means. So first of all, we calculate this AT, right? And this AT is done for a particular word in the context, right? So if we look at our affinity matrix, let me just move this a bit up. There we go. If we look at our affinity matrix here, consider the teeth word in the context, right, which is here. Now, this word has varying affinities with words in the query, right? Like, some of these affinities might be low, some of them might be high, and that's interesting, right? We might want to somehow use that. Now, remember, the affinities are just scalars, they're just real numbers. What we want to do is we want to somehow squash that and get a distribution out of it, right? To sort of standardize it. And the way we do that is using a softmax. So we consider the teeth row, the teeth word in our context embedding. We look at how it matches to every one of the words in the question embedding. We take the softmax across that, and we'll end up with a distribution which adds up to 1, and it essentially tells us, just like before, how much that word matches any one particular word in the question, right? So, but that's for a single word in the context, right? And now, notice that we're trying to construct this U tilde matrix here. And U tilde will end up being the same size as our context embeddings over here, right? So how do we get to that? Well, for every particular word, right? And remember, U tilde is the same size as a context embedding. So when I say for every particular word in the context embedding, or for every particular word in U tilde, I'm talking about the same thing. For every particular word in U tilde, or in the context, what we want to do is we have this weighted sum between AT and the jth embedding in the question embeddings, right? Think of this AT as fixed. This sum goes from j is equal to 1 all the way up to capital J. And if you look back to the question embeddings, you are going from j is equal to 1, which is here, all the way down to the very end of the question embeddings. Or if you're looking at the similarity matrix here, you're considering, this T is fixed, and then you're going across the rows, right? So you're taking this affinity, and then this affinity, and then this affinity, and this affinity, and so on. And then what you're saying is take this affinity here, right, and consider, and this is done by multiplication, consider only that much of the corresponding question embedding. So if the affinity is high, then we will strongly consider that particular question embedding.
Yep. And I guess just to reiterate, what U tilde is essentially, it's very similar to another sort of method called match LSTM, in which essentially you have two passages. So you basically have two passages, and the aim is to get from, for everything in the context passage, we want to have an attended weighted sum over the question. So you can kind of see them as like paired together. So for every context embedding in H, we now have a corresponding embedding in U tilde, which is a weighted sum of all of the embeddings in U that correspond, or that have a high affinity with that specific specific embedding in H.
Yep. Or to, again, just to reiterate, right, for every specific word in the context embedding, we now have a weighted sum across the question embedding words. And that's essentially what attention is, right? Hopefully the intuition for why we're doing this is clear, right? So remember, in Squad, we want to come up with a start and end index within the passage. It's not hard to understand why we might be interested in how context words relate to question words, right? And vice versa. Okay, so this is what they call context to query attention. And then moving on, they introduce what they call query to context attention, which is probably where the title of their paper comes from, bidirectional attention flow. So let's just write that out. So query to context attention. Again, let's go over the maths, and then we'll provide the intuition. So in query to context, somewhat differently, it's not quite just the opposite of this. So in query to context, the end result will again be the same size as the context embeddings here, except the emphasis is reversed. So what they do is they say small b is going to be some vector, and it's going to be a vector defined as follows. It's going to be the softmax of a column-wise max of the affinity matrix S, or similarity matrix S, and this is going to be of size capital T, so the length of the passage. Okay, well, what does this mean? Maybe not what the intuition behind is, but sort of what are we doing here? Again, our similarity matrix S is over here, and now we take this column-wise max. So what a column-wise max is, and maybe it's worth redrawing this guy. So just like this. Again, this is J, this is T. And if I take a different color, a column-wise max, and this is quite confusing, but a column-wise max essentially considers every row. And notice if we consider every row of this affinity matrix, we will be considering row vectors, and row vectors have columns. And then we take the max across the columns, right? So what we end up with is components in this matrix which are the maximums within their respective rows, right? So maybe in the first row, the second, you can think of this as the second component is the max, and in the second row, it's the third component, and in the fourth row, it's the 300th. No, sorry, maybe not 300th, but like the 15th component, and so on, and so forth. Now, once you have these column-wise maxes, right? How many of them do you have? Well, you have T of them, right? Because you've gone over the rows and you've maxed across the columns. So you have T of these maxed out components, and now you softmax them, right? So again, some of these maxed out components are larger than others, right? Which indicates that for that particular context word, question word pair, the affinity is high, right? And if you think about it, what is an answer in squad? Well, an answer in squad is just a contiguous list of words between a start and end index. Contiguous meaning it has no breaks. So perhaps in this example here, the correct answer is as follows, right? So, going back to our original passage of text, that might be the population of Kenya, approximately 45 million, right? You would think that the, affinity between approximately 45 million and maybe, the word what, or, well, maybe maybe what is not that great of an example, but one of the words in the question, probably population, is going to be quite high, right? And then so this is sort of an indication that, and then perhaps we should be looking at these three components. Okay, let's soldier on with the maths a bit more. So now we have this b vector here of size t, and now what they say is, okay, well, let's construct a small h tilde vector, which is going to be equal to the sum across t of bt. Remember, b has t components. Capital H, which is the context embedding, the corresponding context embedding t, right? And this is going to be of size 2D. Right, what does this tell us? B here functions very much like one of these a sub t's. B here is a distribution across these affinities here, right? And then what we're saying is we're going to have a weighted sum across the context embeddings here, where the weights come from B, they come from these softmaxed affinities here. And this essentially tells us how relevant a particular word in the context is to answering our question. And then at the very end, what they do is they say, okay, well, let's build a capital H tilde, which is going to be just, which is going to belong to, oop, that's a euro sign. Let's write that out again. Capital H tilde, which belongs to, or which is of size 2D times t. So the same as the context embeddings and the same as u tilde. And the way we get h tilde is just by taking h and copying it over t times, right? Okay, so what does h tilde mean? What are we doing in this query to context section of the model?
The way that I would describe h tilde is it's the attended weighted sum of the context, and it's attended the how much weight that specific embedding gets in this attended weighted sum is based on its maximal its highest affinity with one of the words in the question. So this max here is basically saying, so for that specific word, what is your highest affinity compared to everything in the question? And that's what it is. It's just the attended weighted sum based on your maximal affinity to every word in the question.
Well, I guess what's interesting is relating what these two, so I bring this over here, what these two different components of the model do, right? And I think that, maybe another way of thinking about this is in terms of granularity, that you can probably think of the right-hand side here, the query to context side of the model, as a more sort of global view, right? A global attention sort of across context words, whereas in the context to query, you're actually more closely relating it to every particular word in the question, right? So notice how, for example, every word in the question is considered in context to query, whereas in query to context, we are only considering the max values, right? And that's quite interesting. Another interesting thing about all this in relation to many other attention models is that this is all done in one go, right? So although we do have some context embeddings, the H's from, where is it? There's no H. The H's have disappeared. All right, let's bring this paper down. So although we do have context embeddings and we have question embeddings, and those are calculated using a bidirectional LSTM, we're not actually sort of recomputing attention at every point in time as we're computing these contextualized embeddings using these two bidirectional LSTMs, as might be the case in other attention models. Instead, we give ourselves a bunch of these contextualized embeddings, and then in one swoop, we compute all the attentions in this context to query and query to context steps. Anyway, in the end, we're left with a whole bunch of things, right? So we're left with U tilde. We're left with H tilde. We also have a capital H here and a capital U here. So those are the sort of, I guess, four matrices to keep in mind for now. I guess we can ignore the affinity matrix now that we have U and H tilde. And that's essentially step number 4 complete. So if we go back to the steps that this paper introduces, we've done number 1, 2, and 3, and 4, and now we're ready to move to step number 5, which is the modeling layer. Oh, and I guess before that, I always thought that this would sort of probably go into the modeling layer, but before that, they actually combine H, U tilde, and H tilde into this capital G. So let's just spend some time going over that. So now the question is, okay, we're still quite a measure away from coming up with start and end indices, right? So now we're going to build our way up to actually outputting the start and end index, and we have to start combining all these various terms we've come up with. So what they do now is they say, okay, well, let capital G, let a embedding or a column in capital G equal to some function beta of the corresponding embedding in H, so the context embeddings, the corresponding embedding in U tilde, and the corresponding embedding in H tilde. And then define by beta a function which takes in, I keep doing this, equals, which takes in 3 vectors, so an H vector, a small h vector, a small U tilde vector, and a small H tilde vector. And then what it does, it essentially just concatenates a whole bunch of sort of variations of these. So what it does is it takes the H and concatenates it with U tilde. It concatenates all of that with H element-wise mul U tilde and H element-wise mul H tilde. And
what a monster.
What a monster. I mean, this is, we're reaching peak Baroque here in, in deep learning models. Again, when you first see this confuses the hell out of you. There is only so much, I guess, intuition you can provide for some of these terms. I think that beta here essentially is doing is, remember, we're building this matrix G, and this matrix G is going to be of size, so let's write it down here. It's going to be of size, and this is quite a whopper, so it's going to be of size 8D times T. So those are some quite big embeddings. As we're building our way up towards outputting the start and end index, which is our final step. Even though we've done all this various attention stuff, we've done context to query and query to context, we're still preserving the original bidirectional LSTM embedding H, right? And that's kind of cool, right? So that flows through, it flows across all this other stuff we've been doing, right? So we're still considering that original contextual information coming in from here. Another thing we're doing is we're directly considering U tilde, right? So we take this small U tilde here. And that's pretty much as expected. Another thing we're doing is we're taking H, right? And we're doing an element-wise mul with U tilde. And maybe a good way of describing that is, how does this contextualized embedding H, which knows nothing of the question, how does it interact with an embedding which does know something about the question, right? So this is a way of combining information coming in from the passage of text alone and the way that particular embedding at that particular point in time, the passage of text, how that relates to the question, right?
Yeah.
And then another thing we're doing is we're taking our H and we're element-wise multiplying it with H tilde. And again, this is also quite interesting, right? Because H tilde, as opposed to U tilde, H tilde is actually the same across time, right? Remember that to get capital H tilde, what we did is we took small h tilde and we copied it across t times. So all these H tildes are going to be the same at every single point in time here, right? And that's sort of why I said that this might, you can think of this as sort of a global view of the interaction between the passage of text and the query, right? Okay, so we have this, these giant embeddings, these 8D embeddings here. Let's move on. Let's finally go to step number 5, which is the modeling layer. And this is a very short step. So if I take my black marker here, in step 5, and I guess I'll just write it out as step 5. They call this the modeling layer. What they do is they take G, they pass it through a bidirectional LSTM. And the result of that is M. And whereas G is 8D by T, M is 2D by T, which is the same as the original context embeddings up there. So this is an example where we definitely are using a bidirectional LSTM to compress the information, right? And you could argue that that compression of information is also, through virtue of being a compression of information, is also a sort of a mushing up of these input vectors to this bidirectional LSTM, which is this, right? So we're looking at all sorts of interactions between these input vectors and then the hidden states of the LSTM which they produce. And we end up with something which is substantially smaller than what we gave to this bidirectional LSTM of size 2D by T. So that's the modeling layer done. That's all they do in the modeling layer. And now we finally get to the output layer. Again, to reiterate, what is it we're trying to do? We're trying to come up with a start and index. So if we have some word and some other word and a slightly longer word and a wiggly word and some other word, then perhaps given some question, the answer in this passage of text is as follows, right? And the way we signal what the answer in the passage of text is by coming up with a start index and an end index. And they actually call this P1 and P2. So point 1 and point 2 probably. Now, how do they come up with P1 and P2? Okay, well, what was the last thing we had? Well, it was this M matrix, this list of embeddings, M. What they do is as follows. For P1, they say that P1 is equal to the softmax of some parameter vector Wt, and they say this is the parameter vector corresponding to P1, so we can differentiate it from other parameter vectors, of the concatenation, the sort of time-wise concatenation of G and M. And again, notice how just like before, we were bringing in information from a step which wasn't the previous step. Again, this is the case in this step. We bring in G, which we actually got at the end of step 4, all the way up here. And we also bring up M, which we got in the modeling layer in step 5. And we concatenate the two. And I think that if you actually look at the dimensions, if you're implementing this, it's always good to check your dimensions to see if they correspond to the paper. So in this case, this guy here would be of size 10d times t. Now notice that it's of size t, right? Which means that it's the length of the passage. And what this softmax does is it gives us, and t is usually like, I can't remember exactly, but it's usually like 300 or something. So we softmaxed across something of size 300, which represents the words in our passage. And then we pick the value, the maximum value, right? And that's sort of what our start index will end up being. But P1 is still just a distribution across what do we think are start indices. P2, on the other hand, and the cherubs, the Baroque cherubs, come flying back. P2, on the other hand, is also a distribution, this time for the n index of some parameter vector Wt P2, again to differentiate it, of G, just like before, and M2. And what is M2? M2 is, the way we get M2 is we take M, we take M, and we pass it through a bidirectional LSTM.
Who would have guessed?
Who would have guessed? And we end up with M2. And this is what the softmax is across then, right? I guess perhaps the intuition here is that you kind of want to, perturb the space so that your weight vector here is working on information which is, suitably different so that you don't confuse yourself. Whoa.
So shall we do a lightning run through it all over again?
Yeah. Let's do it.
So you have your context, you have your question, you have your sequence of atemporal embeddings. You then make them temporal by putting them through a bidirectional LSTM. So you have your contextual embeddings H and U. You then build an affinity matrix with this parameterized affinity function, which is a highway network, right? We then have our affinity matrix. We then use a match LSTM style attention to build a attended weighted sum for every word in the context with respect to the question words. And then we build a global attended weighted sum of the context with respect to all of the question words. All of this happening with these crazy concatenations with element-wise multiplications. We then produce a massive matrix G, which is the same length as the context, in which we just concatenate everything under the sun that we have that's also of length T. We then get that G, put it through another bidirectional LSTM, and we then use the concatenation of G and M to look at to find P1, and we find P1 by concatenating G and M and then collapsing it with a parameterized vector, and then we find the end index by getting M and G, but it's not M, it's M2 because there's another bidirectional LSTM out of nowhere, and then we collapse it with another parameterized sum to get P2, and that's it.
And that's it.
Wow, it's like Wallace and Gromit, right?
Yeah.
It's crazy.
I mean, I guess hopefully if you're still listening by now, if you're not either asleep and the video's still playing, which I think would be great because I fall asleep to a lot of YouTube videos. It's a great strategy for going to bed. Or if you've just quit and in which case you're probably not listening. But if you are listening, then this
congratulations.
Is it. Congratulations. This is it, guys. This is all there is to this paper. Goodbye. Actually, no, wait. Let's go over.
There's some pretty nice visualizations.
There's some pretty nice visualizations, right? So let's go over some of the
and then we won't waste any more of your time.
Yep. Oh yeah. By the way, the results are great. If you go up to the leaderboard even today, you'll see the bidirectional attention flow model right up there. Okay, so squad, right? Experiments in squad. What have they done? I think probably the first interesting thing to look at is table 1, which is where they begin with their results. And this is essentially where they, bidirectional attention flow here. Oh, interesting. As an ensemble beats everything else, as not an ensemble is sort of as state of the art when this was published as you can get. Yeah, their model performs very well. I think that's pretty clear. If you're interested in squad, we'll link to the original paper so you can see how it is exactly it's evaluated. It's non-trivial. These are some other sort of interesting results. So they show that in this figure T2, it's split into 3 sections, A, B, and C. And in A, they t-SNE a couple of things, and it says the t-SNE visualizations of the months names embedded in the 2 feature spaces, the contextual embedding layer is able to distinguish the 2 usages of the word May. So May can either be a month, or it can be a word which indicates whether or not you're allowed to do something, or whether or not something might be like something. You can see that if you actually visualize some of the embeddings, you'll notice that the model learns to separate the month May from the other meanings of May down here, which is kind of cool. It shows that this model is definitely learning something. Another thing that's really interesting, it's probably the most interesting thing, is this visualization here in figure 3. What's really cool about figure 3 is, and you'll notice that a lot of publications which deal with attention will have these attention visualizations, which are just the visualizations of those sort of attention weight distributions, right, which are used throughout the model. If we read the caption, it says the attention matrices for question context tuples. The left palette, so over here, shows the context paragraph, so the passage of text. And there are 2 examples, right? So example 1, example 2. The correct answers are in red, so you probably can't see that, but if you look at the actual publication, you'll notice that those are indeed the correct answers. And then the middle palette shows the attention matrix, where each row is a question word, so each one of these rows represents a question word, and each column is a context word, right? So given a question word, this is attention over the context words, and that's pretty standard. That's very normal in an attention publication. And then comes the interesting bit, and then they say, and the right palette shows the top attention points for each question word above a certain threshold. And if you read the first 2 questions, so if you read the first question, if we only consider the first example, it says where did Super Bowl 50 take place, right? And if you read the passage of text, you'll notice that the Super Bowl 50 took place in Santa Ana. If you look at the words corresponding to that particular point in time, as relates to the question, you'll notice that next to where, And if you know about sort of, a lot of questions in natural language are WH questions, like, where or what or why. You'll notice that next to where, we almost get the full, we get the full answer in a couple of other things. So it says at Stadium Levi in Santa Ana, right? And I kind of find that pretty fascinating, right? This is very much related to what we were talking about, here, where, the answer appears contiguously in these, maxed out components. If you cite some of these maxed out components, I haven't actually looked into this in detail, but I'm supposing that that's what they're doing. You'll notice that, especially next to where, so if this was where, you'll notice that the right answer often pops up, right? And that's kind of cool. And remember, if you're thinking, well, where here is kind of a generic word, like why would we associate where to Santa Ana in particular? Isn't that kind of confusing? Remember that this isn't just an embedding of where, it's a contextualized embedding of where, right? So this embedding of where, which we're then using for our affinities and so on, actually has information about its context, i.e. it probably knows that this is a question, this particular where probably knows this is a question about the Super Bowl. And that's kind of cool, because it gives you sort of not only an intuition of how this works, but also it sort of visually confirms to you that it does indeed seem to work. And then if you read on, they then apply this model to a couple of other data sets, and that's essentially it.